Hello, class. Continuing our discussion of optimization problems, and in this video I wanted to do a couple optimization questions that involve building a box. And so usually when we're building a box, we're given some constraint, and our goal is to make the maximum volume that you can have for the box. So in this case, if you want to build a box with a square base, you're going to see that phrase a lot. That means the length and width are equal. Is to be made from 300 square feet of material. And so we want to know what's the maximum volume. So we have a thing to optimize. That's the volume. And then we have a constraint, which is that the material is at most 300. So let's go ahead and name the dimensions of the base x. So this box is going to be of dimensions x by h, where h is the height. And so then the volume here is x squared h. Again, I have two x's because we were told that the box has a square base. Now, the bottom of the box and the sides of the box are rectangles, so I know how to figure out their dimensions. Namely, the bottom is x by x, so when I go to calculate the amount of material, it's going to be x times x. And then all of the sides, they're all x by h, so that is 4 times x times h. Now, notice here is where we use the fact that the box is open top. Namely, because the box has an open top, I only have one x by x face of the box. The top of the box that's open, that would also be x by x, but we don't need any material to make that. So my constraint here is that 300 is x squared plus 4xh. And then my volume is x squared h. So I want to, as usual, solve the constraint for one of the variables. So in this case, I'm going to say 300 is equal to x squared plus 4xh. So 4xh is equal to 300 minus x squared. So h is equal to 300 minus x squared divided by 4x. Okay, so that is my height. Now I want to look at what happens to my volume when I plug that in for h. Again, always for these questions, the flow of them is you find the thing to optimize, you find the constraint, you solve the constraint for one of the variables, plug that into the thing to optimize so that you get a one variable thing. So the volume is x squared times h, but h is this. So it's x squared times 300 minus x squared divided by 4x. Now, this I can simplify because one of these x's cancels with that x. And so I will have 300x over 4 minus x cubed over 4. Once I deal with that. And 300 over 4 is 75. So this is really, here is my v of x. It is 75x minus x cubed over 4. So now that I have my thing to optimize, all written in terms of one variable, now we can use this important fact that we called Fermat's theorem, that the maximum has to occur somewhere where the derivative is 0 or at an endpoint. So we'll take the derivative, and it will be 75 minus 3/4 times x squared. And we'll figure out when that is 0. So I'll get 75 equals 3/4 x squared. Multiply each side by 4. 300 equals 3 times x squared. So x squared is 100. So x is plus 10 or minus 10. Although, of course, x is the side length of a box, so it cannot be minus 10. So we want to evaluate the volume at both the endpoints, that is, when x is as big as it could be and x is as small as it could be, and at this critical number, x equals plus 10. So the smallest x could be is 0. So I would have a box that is 0 by 0 by something. That would definitely have 0 volume. I have my v of 10. And so if I look back at my formula for v was this. So this is 750 minus 1,000 over 4, which is 750 minus 250, which is to say the volume of this box is 500 cubic feet. The biggest x could possibly be, you can convince yourself, would be the square root of 300, but that would correspond to a box also with volume 0. So as almost always, but not literally always happens in these problems, the best you can do is in the middle with this. So the question was, what's the largest volume we can get? The largest volume is 500 feet cubed, and that happens when x is 10, and the height in that case is, and so we can go back here, the height is 300 minus 10 squared divided by 4 times 10. So that's 200 over 40, which is 5. And so that means my optimal box is 10 by 10 by 5. Those are the dimensions. Okay. Let's do another question that's slightly different. This is actually slightly more realistic as to how we do this. So here we're going to start with a 10 by 12 sheet of cardboard. And we're going to chop some corners off. And then, after we throw away these pieces, we're going to fold them along these lines. And so then we'll fold this up, and this side will come up, this side will come up, and so on. And so then I'll end up with an open top box again. And so the question is, again, what's the largest volume this box can have? Okay, so again, the thing to optimize is that the volume, which is, and so I'm going to go ahead and write this out. Actually, all of these I'm going to call the amount I'm cutting out x. Note, it has to be the same in all of these corners. These have to be squares, and they all have to be squares of the same size, because if they weren't, these wouldn't fold to fit together. I'm going to call this the width, and I'll call this the length. And so the volume here is the height, which is going to come from this x, times the width times the length. Okay, and I also have a constraint. And where is the constraint coming from in this example? The constraint is coming from the fact that I'm cutting this out of this 10 by 12 case. So actually, I know what w is in terms of x. Namely, w is 12 minus 2x, because I got my width by starting with 12 and hacking off these two x by x squares. Similarly, L is 10 minus 2x, again, because I got it by starting with a side of length 10 and then hacking off two x by x squares. So there's actually two constraints here, one for the width and one for the length, which comes from the fact that actually the volume in this case is three things multiplied together. But conveniently, I can plug these things all back into the volume, and then I will get from this that the volume is x times 12 minus 2x times 10 minus 2x. Okay, and so now I've got my volume down to something that only has one variable in it. And now I have to take the derivative of that, but before I do that, I probably want to multiply this all out to make my life a little bit easier. So this is x times 120 minus 44x plus 4x squared, which is 120x minus 44x squared plus 4x cubed. And so then when I take the derivative, I'm going to get 120 minus 88x plus 12x squared. I can certainly divide everything here by 4 and rewrite this in the usual order. So I'm going to try and set this equaling to 0. So that'll be 3x squared minus 22x plus 30 equals 0. And unfortunately, this does not factor. And so, because this doesn't factor, you're going to need to use the quadratic formula to get this. And so the quadratic formula tells you, remember, that the roots are this, where a is 3, b is minus 22, c is 30. And if you do that, you will learn that there are two possible things, namely x can be, so I guess I just say this, x is approximately 1.81, or x is approximately 5.52. Now, at first, you might be inclined to say, oh, both of those make sense, x just has to be positive. But actually, if you look back at the original question, and you look closely at what x is doing, we're hacking off x, or hacking off two x by x squares from the side of length 10. So actually, if x is 5.52, we're hacking off 11 total from this length 10 side. So that doesn't sound super good. This is not actually a sensible thing. So we're going to get, actually, as our only critical number, this 1.81 number. So then I have to ask myself, okay, what's the biggest x could be, what's the smallest x could be, and then what's this? Well, the biggest x can be is 5, as we just sort of argued. The smallest x can be is 0. But certainly v of 0 is 0, and v of 5 is 0. So that means the largest volume the box can have is this v of 1.81 number. And if you plug this into your favorite calculator, whatever, you'll find out that the maximum volume of this works out to be somewhere in the vicinity of 96.8. And then that would be in feet cubed if you want to pay attention to the units. Well, I'm going to wrap up this video here, but in the next video I'm going to do some more examples of optimization coming from geometry. Until then, though, be well.